Good evening, welcome to the week 2 live session. Hope I am audible and my screen is visible. Could someone please confirm on chat? Great, thank you so much. We'll just wait a minute more today because there was a reschedule and I'm not sure how many people saw it in time. So let's wait a couple more minutes. People seem to be joining. Okay, let's get started then. So welcome once again to the week 2 live session for the GPU Architectures and Programming course. So in case, since course enrollments are still open, how to get these session recordings? Yes, I will cover that just in a minute. So maybe wait for that and still ask me if you don't figure out. So in case any of you are joining this for the first time and missed last week's session, I will cover some of the logistics and administrative stuff, but more shortly this time because last time we went over it in detail. Okay, so let's get started. So you will have 1 2 hour session conducted every week. You will have 13 of these, 12 aligned to the 12 weeks of course content and 1 week for a revision. The typical time is Sunday 6 to 8 pm, but in case of any reschedules like today, you'll get an email from NPTEL. Sorry about the reschedule for today, but I'm traveling the whole of next week, so I couldn't do Sunday. But this won't happen very often. It'll be a one-time thing in your 12 weeks. So what to expect from these sessions? They will be very aligned to problem solving. They are mainly intended to help you solve your assignments and your exam questions and things like that, and also to get your doubts cleared. Since there are a lot of people joining these, it gets a bit chaotic if I leave audio on, so I would prefer to have interaction through the chat box. But feel free to post your questions or doubts anytime, right? I might look at it after 2 minutes, and depending on the content I have planned for that week, I might sometimes tell you that I'll get back to you in the next week's live session, but I'll definitely answer your doubts, so feel free to ask. And yeah, about the recording part, you will get access to both the slides and the recording from NPTEL through an Excel sheet. But I think you guys haven't. NPTEL typically sends that out after a week or two, right? So typically by the second week's live session, you should be getting it. But in case you want to access it earlier than later, I can quickly share the recording for last week. Let me do that right away. But you will be getting access to this sheet from NPTEL officially in your course page itself. So watch out for that, right? That will, I'll also share the slides link directly, but you will get both of these from NPTEL officially. You should be getting it sometime this week or next week. They must be kind of figuring out logistics. But I typically post both the recording and the slides within 1 day of the live session. So in case you have to miss one of these live sessions, you can just watch the recording on YouTube and go through the slides. But I would highly recommend attending it in person because it's meant to clear your doubts and questions, right? And an offline one kind of beats the point of that. It'll be like watching more recorded material. And this is how I structure the live sessions, but I'm open to inputs on this. So we'll have a 30-minute recap of course content, whatever was covered in that week. So it won't be a very detailed one where we cover everything again, but a very brief one where we specifically focus on some topics. Then we'll do a 1 hour problem solving and books for practical GPU programming. Let me see. I think your references did not cover that. We went through that last week, but your references probably did not cover that. Let me check on this and get back to you. I'm not aware of any textbook as such. I've mostly used CUDA tutorials and such. But if anyone else in the audience has a suggestion, feel free to post it in chat. I will check on this and get back to you in the next live session. Yeah. And we'll have a 5 minute break midway. So today around 8 we'll take a 5 minute break so that the 2 hour session doesn't feel too overwhelming to you. And at the end of the session, please let me know if you have any feedback on the session structure. And any doubts in that week's course content also feel free to ask me, right? I will get back to you if I'm not able to answer it right away. So, and you have a discussion forum for people who are not aware of this. So you could ask questions here and then the TAs will monitor this and get back to you. We have another question. Do we need books even after studying all PDFs of the course content? Depends on what you're trying to do from the course, right? So if you're trying to get a more detailed understanding of GPU architectures, maybe you're a researcher and you want to do something there, right? You will very likely have to do additional reading of your own. If you're merely looking to get a basic understanding and clear the NPTEL exams, I think mostly sticking to the course content will be enough. For some things, like last week you would have seen that there was a Compark review, right? So there you saw that some questions were asked outside the course content. There may be outlier cases like that, but most often, I'll say 90% of the time, for your exams and assignments, just studying the PDFs and watching the lectures will be enough. We have another comment. OpenCLs, ICL, CUDA tutorials and GitHub repos are there. Yeah, that's kind of how I have done it too. So so it depends on how you're approaching GPU programming, right? If you actually want to start off doing something. If you have an application in mind, then you look up stuff very specifically needed for that application, and you'll quickly be able to find tutorials and GitHub repos that you can learn from. If you're looking to get a more theoretical understanding of all the concepts in CUDA programming, then you'd probably prefer a textbook, right? So I'll look at that and get back to you. I'm not aware of any as of now because I've also mostly relied on CUDA tutorials. Yeah, so any other questions on the logistics? Okay, people are still joining. I typically start off by 7:02 or 7:03 because I know a lot of you join on time and even before time. So I would recommend everybody to join maybe 1 minute before the live session starts so that we don't have to repeat things again and again. From next week at least, if you could do that, that would be very helpful. Okay. So yeah, I went through this last week as well. So how do you make the best use of these live sessions? Watch that week's lectures on NPTEL and try to solve that week's assignments, right? That way, if you have any doubts, you can immediately ask me, and that will help you make the best of these sessions. Otherwise, a lot of problems that we work out also are based on the assumption that you've gone through the course lectures. So I would recommend doing that. So with that, we are at the end of logistics. Like I said, I'm giving a very quick recap today. In case you want more information on this, the YouTube link that I shared has a very detailed description of all of the logistics. But if you have any quick questions now, we can also take those before moving to this week's content. Any questions on the logistics? I'll give you a minute. Okay, there are no questions and we can proceed. So what we'll do today is, since last week we spent a good amount of time on the logistics, we still have some questions left from last week, maybe 4 or 5. So we will finish that as well as some of the doubts that were asked last week. By the way, last week I had an internet issue, so I dropped off and lost some of the chat history. So in case your questions are not covered today, please remind me again. Throw some light on the toughness of this subject. Yeah, in general, it is probably not a very common undergraduate course, right? Typically, in your undergrad, you probably learn, in a CS undergrad, you probably learn computer architecture and operating systems. This one kind of is probably one level deeper than typical computer architecture because it goes a lot into GPUs, right? But it's a good systems course, especially for people who are interested in the architectural aspects of these things. So for postgraduate or typically this level of courses, right, I always encourage you to do your own reading apart from what is covered in the videos and what is given to you as PDFs. If you don't understand a topic, and it's very likely that you may not, because like for some of you this may be very new and you may not have done a computer architecture overview at all, so you may find some of the concepts a little difficult. But what I would recommend, rather than, I think I think there was one question on the discussion forum asking about how to pick up computer architecture, and what was recommended is to go through a typical textbook for computer architecture. That would take you a lot of time, right? So in case you don't have that much time, what I would recommend is, when you're studying a topic and you don't understand that topic, quickly refer to it, right? And you will find these covered in a lot of masters and undergraduate courses and a lot of lectures that are online. So that will help you understand the topics better, and it may be a little overwhelming in the initial weeks, but after you get a hang of the basic concepts and CUDA, I think it should be better. So don't worry too much about it, and this live session is meant to help you out. Is it easier or tougher than machine learning? Okay, so it depends on how you look at machine learning, right? If you're looking at applied machine learning, where you just want to develop some applications, then that's a lot easier, because mainly because of the community support on the internet, you find a lot of code that you can simply take and run, right? So that's that side of it. But if you're looking at theoretical machine learning, not really. It involves a lot of math fundamentals and sound understanding of linear algebra and things like that. So that's very different. From this side, I would say it's comparable to an advanced systems course, right? Maybe advanced computer architecture or something like that. So don't worry too much about the toughness of it. Try to focus on every week what you understand and what you don't understand. So if you don't understand, bring it up in that week's live session, and then I will probably give you some additional resources that make it easier to understand the topic. For instance, last week we did that for pipelining, right, where we had a laundry example. So a lot of these concepts might seem very difficult or daunting when you look at it for the first time in a very abstract sense, but what always helps is to look at real world examples. So we'll try to do that whenever you guys have trouble understanding a particular topic, but don't let the toughness of the subject discourage you too much. That's my answer. How benefiting will it be for an electronics student? Again, depends on what you want to do, right? So this will give you an understanding of the internals of the GPU and also a good amount of CUDA programming. So if you're looking at writing CUDA programs or parallelizing stuff and things like that, it will definitely help you. As an electronics student, I don't think it's part of your core course curriculum, but if you're interested in systems, I think this would be a very good course to take. Yeah, you're welcome. Okay. Yeah, it's not part of your core curriculum, so it has to be out of your own interest and what you want to learn. But it's a good systems course, and there are very few of these, right? Computer architecture, you might find a lot more, but GPU architecture is again more niche than that, so you might find fewer courses out there. Okay, with that, we will move to last week's questions. Sure, you're welcome. Yeah, so like I said, I've tried to capture most of your doubts, and some of them I've kind of made a note and I'll cover it in the next week just due to lack of time. But in case you don't see your questions either covered today or listed for next week, then please ask again. Okay, so somebody brought up this concept of cores and threads, right? What is a core versus what is a thread? So this is a good sort of abstractions and interfaces to be aware of. Again, I'll cover a bunch of these in the live sessions that are not directly relevant to the course, but I think they will help you in your understanding of the whole system side of things, right? So whenever I present something like that, I will title it key concept. So it's meant to be generally useful to you, but it's not directly relevant to this week's course content. And similarly, I will have things called asides, which are again outside the scope of the subject and maybe not even generally helpful. But if someone is curious about something and I have the time, I would still be answering those questions. So make a note of these things. You don't have to worry. If you're looking at just covering what's needed from the NPTEL exam point of view, you can skip some of these things. You don't have to understand them too much in detail. So these are basically abstractions at different layers, right? So the ISA or the hardware abstraction layer is a very low level, whereas the POSIX or the interface at which programmers typically look at things is a higher level of abstraction. So if you're talking about compute resources, at the ISA level, you will often see people referring to these as cores, processor cores, CPU cores. But if you look at it as a programmer, you will talk about processes and threads. Now, both of these are referring to compute, but at different levels of abstractions. So this is something to be aware of. Similarly, if we talk about memory, you will hear physical memory or RAM, right? And at the programmer's level, you typically hear of things like address space or pages, paging, things like that. Similarly, when you talk about storage, what's actually there on your hard disk is blocks, hard disk blocks. But what is exposed to you is actually a file, right? So for those of you who use Windows, you would have opened your Windows Explorer and you would have seen all these files. But if you go one, that's a form of abstraction. But if you go lower, if you go closer to the hardware, what it actually maps down to is a hard disk block. And similarly, here are some more examples listed. But since this notion is not very core to this subject, we won't go through them in detail. This is just something for you to keep in mind. Whenever you hear a term, think about which level of abstraction it is meant for. That will help you understand things better. Okay, another question I got was the relation between ILP and pipelining, right? How different are they? How similar are they? So ILP refers very broadly to simultaneously executing multiple instructions from a program. And pipelining is a form of ILP. So last week we saw pipelining in detail, spoke about latency, throughput, spoke about the 5 stages of pipelining. But as you studied in week 1, there are other strategies for ILP, right? Things like VLIW, etc. So ILP and pipelining are not the same. Pipelining is a form of ILP. That is the difference. Okay. The other question that I got was on register file. So these are registers that are actually part of the CPU, right? And they're actual hardware registers. Somebody also asked me about software registers. Now this, again, I've listed it as an aside. So note that you don't really need to know this from the perspective of the course. But just for curiosity, there are things called memory mapped registers or software registers, right? So these are not hardware registers in the sense that they're not made from flip-flops or something like that. It's just a memory location that is kind of exposed as a register. So typically IO devices have these, and drivers, read and write values from here. So I think the person who asked this question was talking about GPU kernel mode driver and how to wake up the graphics it writes to a particular register and so on. So those are some typical use cases of software registers. But again, from the perspective of this course, it's not very important for you to know. So yes, so those are a few questions I am covering this week. Next week, one second. And again, this is just due to lack of time, right? Because we need to cover a bunch of assignment questions from last week as well as assignment questions from this week. So what I'll do is all the caching questions that came last week, right? Terminologies like cache hit, cache miss, penalty. And we had a question on CPI that people were not so clear about. So those two things we will cover next week. I also said that I try and find a ComPark primer or a recap source, because a lot of you, I presume, don't have the time to go through a computer architecture textbook entirely. I didn't get the time to do that, so I will also do that this week and list it in next week's slides. But apart from these, are there any other questions or doubts with respect to week 1 content? Please ask in chat. I'll wait a minute. Again, I'll probably cover them next week, but from your side, please make sure you ask your questions. Anything I missed from last week that you asked and that was not covered, again, please post it in chat, because I lost some of the chat history last week. I went through the recording and got some questions, but feel free to ask again if it wasn't addressed. Okay, I'm guessing there are no other questions. Okay, in that case, we will move on to the problem solving. Again, we had a few problems left over from last week. So we'll try to finish up with that and then move to the week 2's content. So again, this is the interactive part of the session where I expect all of you to solve these questions and respond on chat with your answer. Again, it's not any kind of an exam or an evaluation where I'll be scoring you for what you answer. So don't worry about getting it wrong. Feel free to answer even if you're confused or not sure, because that will help me understand what I need to emphasize better. Okay, so let's move to the first question. Dash type of computer architecture aims at reducing the time of execution of instructions. CISC risk. Okay, the answer is already highlighted, my bad. Okay, risk. Okay, since we already have the answer, let's go through a brief difference of CISC and RISC. So again, CISC is the older, more traditional ISA, which had a lot of complex instructions, right? The length of the instructions could vary, and they could take a lot of cycles and so on. RISC is kind of a new idea that emerged, and even today you'll hear of RISC-V and things like that. And ARM processors typically are all RISC architecture based. And here, every instruction takes a single cycle. So we don't want to have multi-cycle instructions or complicated instructions. We want to have a small number of fixed length instructions, very few addressing modes. So overall, you can think of it as a simpler architecture. So going back to the question, RISC aims at reducing the time of execution of instructions. Of course, to compensate for something like this, you would have to write more instructions, but it helps in a lot of other things by keeping the instructions simple. So is that clear? Any questions on this? Okay, if not, no questions, great. A 16-bit address generates an address space of dash locations. You have 4 options. Two to the power of 16. Okay. Anybody else? Anyone else? So the others who are quiet, what's kind of the difficult part of this? Do you understand what is an address space? Are you having trouble understanding the question? Okay, we have another answer, 65,536. Anybody else? Okay, 65,536. Okay, looks like most people have been able to calculate it. The answer is 65,536, and it's simply 2 to the power of 16, right? You understand it? Okay, great. I will still give you a quick explanation. So if you have a 2-bit address, for instance, you could represent 4 things, right? Because this could take 2 values and this could take 2 values, and you would have 2 to the power of 2, 4 values. Similarly, if you have 16-bit address, you would get a 2 to the power of 16, which is 65,536 locations. So it's very simple. Okay, so we'll go to one last caching question. Any other questions, anyone else, before we move to this? Okay. If not, let's look at this question. So again, the data is common from 11 to 13 questions. So consider a computer system with 16-bit memory addresses. If the 2K byte cache is organized as a two-way set associative cache that uses the LRU replacement algorithm with 16 bytes per cache block, assuming that the size of each memory word is 1 byte, calculate the number of bits in a word field of the address. You can take 2 minutes to calculate this. Week 1, question 9 answer is not there in the answer. So, are you referring to the official assignments from NPTEL? Okay, I haven't looked at that. So, when is the deadline for this assignment again? 7th Feb. Okay. So typically, if you see cases like that, feel free to ask in the Google group or the discussion forum, and I can take a look at it. But I am only permitted to answer the question after the assignment is officially submitted. So I won't be able to tell you if it's right or wrong. But typically, if an answer given does not contain the right option, then typically NPTEL will account for that, as in they may give you extra marks, or they might not. They might give everybody marks for that question, or they might remove that question from the grading, and so on. So don't worry, just make sure that from your side the calculation is correct. And if you, since you have 5 more days, if you're confident that the answer is not there, please post on the discussion forum. So apart from me, there are regular TAs for the course who kind of frame all of these questions and have the answer keys. So they will look at it and get back to you. Okay, so sure. So answers to this question. Anybody? Was the 7 an answer to this question, or the answer to when the deadline is? Any answers to this question? I'll give you another minute. You can take your time to solve it. Okay, B5. Okay. Any other answers? Okay, let's. Do you need more time to solve this, or shall we look at the answer? Okay, we have one more answer, 4. So I'm guessing people are still solving. Let me give you a minute. Any other answers? Okay, maybe this is a bit confusing. So, like I said, I will cover the cache concepts next week. So, we'll go through what is set associative, fully associative, direct mapped, and things like that. And then maybe this will be clearer. But the answer is 4, and you're given that each cache block has 16 bytes. So basically your block size is 16 bytes or 2 to the power of 4 bytes. So a word, remember that I had this diagram in the last week's live session. So if you don't understand this, one thing I'd recommend is to go watch that video where I tell you how you understand logically this word bit and the tag bit and things like that, right? So this one is about the offset where within the cache block. And again, why I tell you to understand it is once you get it logically, when you understand the rationale behind these fields, it's harder to make mistakes, right? Rather than just trying to remember how to do it. So I would recommend going through that, but broadly the idea is you're trying to find the offset within that block. So you would need the block size is 16 bytes or 2 power 4 bytes. So you would need 4 bits to get to the offset. Hope this is clear. Okay. Don't understand why set index is in the middle. Okay, again, I think that will be clear once we cover the set associative part, but I'll make note of your question and specifically address that when I do the recap next week. Okay, we will move to the next question. Calculate the number of bits in a set field of the memory address. So your question is why is this in the middle? It can be either on the other side or the way the cache address is formed, right? Okay. And do you think it would change things? For instance, let's say we swapped the word and the set field, right? Do you think that would have any implications on caching? Or do you think it's just convention? Like people have chosen this and then they're just sticking to it for a standard reason. Okay, we will cover it in detail next week. So hopefully after that you understand. If you don't, ask me again. Okay, any answers to this? Number of bits in a set field of the memory address? Six, okay. Please show data, sure. Yes. So the question is number of bits in the set field. Any answers? Okay, we have an answer saying 7. Another one saying 4 and another one saying 6. Okay. Another one saying 6. Okay, I think all of you have had enough time. So let's look at the answer. So the data given is two-way set associative and 2K cache. 16-bit addresses, and size of each word is a byte. So the answer is 6. So let's see how to get to the 6, right? So the cache size is 2 KB, which is 2 power 11 bytes. And the two-way set associativity basically refers to the number of cache blocks per set, which is 2. So basically, to get the number of bits in the set field, you need to get the number of sets, right? So cache size divided by block size into number of blocks per set. So in the direct mapped case, it used to be just 1, right? So cache size divided by block size would give you number of blocks. Now you're saying there is a two-way set associative mapping. So cache size divided by block size into number of blocks per set. That's kind of, screen is not visible. Is that for everyone? Because I see it being shared. Is visible. So if it's not visible for one of you, then I think there's an issue with your meet. So please try and rejoin, and that should fix it. Yeah. Okay. So going with this formula, so cache size is 2 power 11, the block size is 2 power 4, and 2 blocks per set. So this becomes 2 power 5. 2 power 11 divided by 2 power 5 is 2 power 6. That's your number of sets. So number of bits in the set field is 6, which is option C. Again, if you don't understand set associativity very well, this may be confusing, but let me cover this in the next week's session, and then we'll probably take a look at one caching question again, so that you're very clear on that. Hope that helps. And the last question in this set, calculate the number of bits in a tag field of the memory address. 4, 5, 6, 7. Any answers? Six, okay. Anybody else? Six, great. Anyone else? We'll wait for a few more seconds and then look at the answer. Okay, we have one more answer saying 6. Great, okay, this part at least seems to be easier than the rest. So yeah, tag field, there's always a shortcut. You could do the total number of bits minus the other two, right? So 16 minus 6 minus 4, which gives you 6. So that's the answer for that. Any other questions on caching? Anything that you don't understand, please mention it specifically. We will cover caching in detail next week. Okay, if no other questions, we will move to the last question from last week. So this one I'll give you time and you can tell me what you think is the answer, and then I'll discuss it next week. I don't want to spend too much time today on last week's questions. So a branch predictor is a digital circuit that tries to guess which way a branch will go. The purpose is to improve the flow in the instruction pipeline and play a critical role in achieving high performance. Let's assume that series of outcomes in a particular branch when it was getting executed within a loop is given. And these are the outcomes: true, 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 not true, 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 not true, again 3 trues, and not true, not taken in this case. Assume that the branch predictor always predicts not taken. So what is the percentage of misprediction? 20, 25, 50, 75. This should be an easy one. I'll give you 2 minutes, take your time and solve it. 50%, okay. Anyone else? So notice that this one always predicts something. It has no notion of history or statistically what was the decision and things like that. So it's a very simple thing. Whenever you ask it, it will say, I predict that the branch will not be taken. We have another answer, 25%. Anyone else? 75% misprediction, okay. 50, okay. 50, okay. Okay, we will discuss the answer next week. So with that, we will move to the week two's contents. But before that, I'll give you 30 seconds. If there's something that's still not clear in week one, please ask me now. I'll cover it in the next week and we'll make sure we close out on week one doubts and questions. Anything that's not clear. It could even be an assignment question that you're finding it tough to solve. Of course, I can only discuss it after the deadline, which is 7th. But the next week's live session is after that, I'm guessing. Yeah, it will be on 11th, so that's perfectly fine. So if you have any doubts or questions, now is the time to ask. Will this be available? Yes, as I mentioned at the beginning, all recordings are uploaded to YouTube and the link will be sent to you. So yes, it will be available. Any other questions or doubts from week one? Sure, you're welcome. Okay, if not, let's move over to week two. So here we started with an introduction to GPU architecture. We looked at vector parallel processors, data parallelism, SIMD versus SIMT, and we started talking about GPUs and how originally they were intended for graphics tasks. And we went through the graphics pipeline. We looked at the Tesla architecture, the ISA of the GPU, the memory hierarchy, which was something we were talking about from the perspective of the CPU last week. But in week two, we also looked at it from the perspective of the GPU. Then we spoke about integrated GPUs and mobile and embedded GPUs. So we will cover some of these in a very quick recap today. And but if something from this list is unclear to you and you don't understand it very well, please ask your question on chat and we will specifically cover that topic in more detail. Okay, so we'll start off with the graphics pipeline. So this is what it looks like. There is an assembler followed by the vertex shader, geometry shader, and the rasterizer, the pixel shader, and the final output merger. So we will look at briefly at what some of these things do. Again, this is from a very historical perspective, right? What the GPU was intended for, what were these graphics operations, and how things used to happen. Again, from using GPUs today, this might not be very relevant to you because most of you use it for computing, not really for graphics tasks. But if there's somebody who's more interested in this side, then we'll talk briefly about this. So a graphics application sends the GPU a sequence of vertices grouped into geometric primitives like points or lines or triangles. So remember, the first stage was the assembler that collects these primitives, right? Then you have the shader, which maps the position of the vertices onto the screen, and it does alterations as needed, alterations on color, position, or orientation. Then you have geometry shader, which operates on geometric primitives, and again this works on changing them or generating additional primitives. And a little more of these details we will go through in your assignment questions, where there is particular focus on some component. But for now we will stop at this and move to the other part of it. So again, like you see, GPUs are everywhere, right? Apart from the server grade or desktop GPUs, there are integrated GPUs, right? These are basically, so if you buy a laptop, you will typically have to make the choice of whether to get a discrete GPU. So when I say discrete GPU, it is actually connected through a PCIe bus to the CPU. And typically these discrete GPUs come with their own RAM. So typically that's called graphics memory, or you'll see DDR4 this much or something like that, right? And or so those are that memory is dedicated for the GPU. But when we talk about integrated GPU, so suppose you buy a laptop without a discrete GPU, by default there is a GPU on it, right, in most systems. And that's what's called an integrated GPU. So this is where it's not plugged in through a PCIe bus. It is it's kind of on the same system on chip, and the CPU and the GPU share the same memory. So let's say you buy 16 GB RAM, it's not just CPU RAM, right? Because there's no dedicated GPU as such, and there's no dedicated GPU RAM. So they both share the same physical memory. And you have some things that can facilitate zero copy transfers. Again, because this is the same physical memory, so you can get some benefits out of that. And again, the problem is if you have one single memory unit, and your CPU and GPU are typically compute units, right? So think of it as let's say a CPU and a GPU, and these may be running two different things. But now the contention comes from memory, because both of them are going to try accessing the same RAM, and the GPU application may be very high, may need very high bandwidth, and this makes kind of starve the CPU application, right? So the bandwidth would be shared between them. So that's one of the problems of an integrated GPU. Now apart from this, you also have mobile GPUs. You would have heard of the Mali GPU or the Adreno GPU. Again, these are meant to accelerate graphics as well as compute tasks. You'll also see embedded or edge devices like the NVIDIA Jetsons are a prominent class here. So you'll see a number of these platforms with ARM CPUs and then NVIDIA GPUs, and some application specific integrated circuits or ASICs, which are meant to improve deep learning tasks, right? And you also have one range of GPUs for the autonomous vehicles, which support a lot of ADAS functionality. So again, these are all the different segments of GPUs from the perspective of where it is deployed, right? Apart from this, obviously you have your workstation, your server grade GPUs. And by the way, someone was asking me about access to a GPU, right? So I briefly looked it up, and I think Google Colab has access to a free GPU. So try that out if you want to run GPU programs, and if that doesn't work, ask me. I can take a more detailed look. In case you don't have a GPU, I think that's what the person who asked the question wanted to know. Okay, so this is about the different classes of GPUs. And with that, we move to the problem solving. So before that, again, today's recap was very brief because we had a lot of territory to cover from last week's questions, and we also have this week's set of 10 questions. So we've kept it very brief. But before we move to the problem solving, any doubts or questions in week 2? Anything? I'll give you a minute. Think about it. Another thing you could do is in the 5 minute break that I give you, you could kind of go through very quickly your notes or something like that. See if you have doubts on anything and then ask me when we come back. That's also okay. So maybe we should do that and take our break a little early because I think we have 10 or 11 questions from this week. But logically now is a good point to take a break. So it's 54. We will resume at 7:59. But if you have any questions or doubts, please make a note of it and post it on chat. I'll keep the call running, but feel free to join back at 7:59. Okay, let's continue. Any other doubts or questions that you guys came up with? Please post it on chat. If not, we will move to the problem solving part of today. One human architecture is not suitable for realizing SIMD. True or false? Take a minute to think about this. Any answers? How many of you don't understand what is SIMD? Then this question may be tough. So I'd just like to get an idea. If you don't understand SIMD, then we can explain that in the next class. We have one answer saying true. Okay. Anybody else? True. Okay. True. Single instruction, multiple data. Yes. But I meant more about what that means or how that translates to architectural features, right? So here you're being asked about whether a particular architecture is suitable for SIMD. So for the people who said true, just curious, how did you come to that conclusion, right? What makes you think that it's not true? Again, it may be something that you just read, right? That's also okay. But I'm just curious to understand if you how you think it is true. This is also something we can briefly talk about in the next lecture if some of you want to understand more on what SIMD means, etc. Yes, the answer is true, and it has a common memory unit, right? So it's basically going to use the same thing for instruction and data. So that's kind of the reason why it's not suitable for SIMD. But if you guys don't understand this very well, I'm happy to talk about it in detail. Just drop a note on chat. Okay. If not, let's move to the next question. Oops. Vector processors can handle data level parallelism. True or false? True. Okay. Yes. Okay. True. Anyone else? True. Okay, let's look at the answer. It is true. So let's see why that is, right? So again, here is one of those things that's not very relevant from the course itself, but more generically, it's useful to understand the difference between data and task parallelism, right? These are dimensions of parallelism. So in data parallelism, you distribute subsets of the data against multiple cores and you execute the same operation on each of them. So in this case, you can see that there is a task 1. Think of this as some sort of maybe addition, right? And you take your data and you distribute it this way. So a simple example could be, let's say you have two arrays and you want to do some kind of element wise addition. So I will distribute the data such that maybe each of these cores operate on two elements, right? So the task is the same, the addition of two elements, but the data is being split. So that's data parallelism. And then finally you would have an aggregation task. And similarly, There is task parallelism, where you distribute the tasks and you kind of have a different operation on each task, right? The data is the same. So for instance, I could take the same array and maybe compute the sum of it, the mean of it, and something else that's unrelated, right? So each of these operations could be different tasks, but here, unlike in data parallelism, it's not the data that's split, it's the task that is different. And then you might have an aggregation task as well, depending on what your application is. So these are two different types of parallelism. So even in things like neural networks, which you'll study later in this course as an application to GPU computing, you will see the same notion of data parallelism, where people will talk about splitting the training across multiple GPUs. And there is also this notion of task parallelism or model parallelism. So this is in general a very useful notion to understand. So whenever people talk about parallelism at an application level, ask yourself if it's the task that's being parallelized or the data that's being parallelized. Any questions on this? Okay. If there are no questions, let's move back to the actual question, right? So in terms of data parallel algorithms, there are various architectures or various hardware that supports this, right? GPUs and SIMD and vector processors. So you were asked about vector processors and whether they support data level parallelism. The answer is true, again because of the way they are designed. Hope this is clear. Next question. Vector processors contain only vector registers. True or false? False. Okay. Anybody else? False. Okay. False. Any other answers? Okay. If not, we'll take a look. It is false. So again, vector processors do have vector registers, where each vector register is a fixed length bank holding a single vector. And you have other functions also, like your functional units are vectorized, but you also have original scalar registers. For instance, yeah, here there's an example of VMIPS, which has 8 vector registers, but in vector processors, the scalar registers are also retained. So the statement that they contain only vector registers is false. I think this is clear to all of you from your answers. So we will move to the next question. When we say vector in vector processors, is it really a matrix of 0, 1, say a floating point stream, or linear B1, 0, 1 vector? Okay, again, some of these questions will be useful with an overview of what a vector processor is, right? So again, I'll take it up in the next class and explain this. Thanks for asking. Okay, we'll move to the next question. Tesla GeForce 8800 has a total of 128 SPs organized in 8 SMs. State true or false. Again, this is memory based. You either remember it or you don't. But for those of you who remember it, any answers? True, okay. Anyone else? True. Okay. Anyone else? Okay, I'm guessing the rest of you don't remember. So we look at the answer. It's actually false. So it is organized as the 128 SPs part is correct, but it's organized as 16 SMs and not 8 SMs. So that's the correct answer. And again, there's no particular reason for this. It's how that GPU was designed. That's all. Okay. Before we move to the next question, any doubts so far other than what you guys have already asked? If not, we'll keep moving. Cache memory and constant memory are unified for all streaming multiprocessors. True or false? Any answers? True. Okay. True. Okay. Any other answers? Okay, let's take a look at the answer. Again, this is false. So let's take a look at. Thank you for your concern, but yeah, I haven't had the time. I had to prepare for today's lecture, and I'm traveling. So yeah, we'll get to that after this. So each SM has its own cache memory, which is used to store intermediate data generated during computation. And this cache memory basically helps reduce the number of global memory accessories, which would improve performance, right? So anytime you have memory on chip versus off chip, you'll hear this a lot. It helps, the on chip memory is obviously faster and it helps performance. So every SM has its own cache memory. So this is kind of false. Cache memory is unified across all streaming multiprocessors. And constant memory is a special type of memory that is used to store constant values required by the GPU kernels. Unlike cache memory, constant memory is not local to an SM but rather is global memory that is shared across all SMs. So that's the difference between the two. Again, I'm not sure if this was directly addressed in the course content, and this whole memory hierarchy of the GPU is also it may seem very confusing in the beginning. So if this part is not clear, please let me know and we can talk about it in detail in the next week's session. Please elaborate. Yes, we'll do that. We'll do that in detail in the next session. We'll talk about the whole memory hierarchy from the perspective of GPUs. Okay. The next question. Dash maps the position of vertices onto the screen, altering their position, color, or orientation. Again, we briefly discussed this at the beginning of the session. Any answers? Pixel shader, B, okay. Pixel shader. Anyone else? Vertex shader, okay. Vertex shader, okay. So yeah, the answer is vertex shader. I think we looked at this very briefly in the beginning. So yeah, the vertex shader maps the position of vertices onto the screen, altering their position, color, or orientation. And if you look later in the pipeline, there is a pixel shader. From what I remember, the pixel shader is, it kind of takes the output of the vertex shader and then adds, then figures out things like the color of a pixel, etc. So it's kind of similar in some aspects. It's just that it comes later in the pipeline and it does operate on a pixel. So the answer to this question is vertex shader. Moving to the next one. Dash fills the interior of primitives, including interpolating per fragment parameters, texturing, and coloring in graphics. Pixel, okay. Anyone else? Geometry, C, geometry shader. Pixel shader, geometry shader. So again, I think these are very confusing for most people. So I'll try to see if I can find an example. I again haven't, I'm not familiar with the details of the graphics pipeline. So we have another answer saying geometry shader. Okay. So, but I think going through it in terms of an application would be very helpful. So that's something I'll try to do for the next class. But the answer is pixel shader. Again, let's look at what was there. I think pixel shader was not really explained. But for people who answered geometry shader operates on geometric primitives and it changes them or generates additional primitives. And what was asked here was, okay, this, yeah, this was again interpolating. We went through this. Yeah, so this is about the interior of primitives and then texturing, coloring. So that's your pixel shader. So next question, again I think this is obvious having covered the other two. Dash operates on lines and triangles defined by multiple vertices, changing or generating additional primitives. Geometry, geometry, Geometry. Okay. Does this have anything to do with normal computation, or are these taken from? These are completely from graphics, right? So it's kind of like the history of the GPUs. Uh, when initially GPUs were intended primarily for graphics, not really for compute. So in those days, the graphics pipeline was comprised of these operations. The graphics pipeline still is there. So any rendering and things like that that the GPU does, you will still hear of these terms, things like hull shader, vertex shader, and but the terminology is definitely from the graphics side and not the compute side. Okay, the answer to this is geometry shader. Like I said, to help you not get confused between the three, I'll see if I can get you an application that shows you this end-to-end pipeline that will help you understand better. Okay, Dash is the world's first GPU. You have four options. C, okay, 256B. Anyone else? B, 256. 8800. Okay, let's look at the answer. The answer is 256. Again, this is a factual thing, so you just need to remember it. It's a recall based question. Okay, the next one. Tesla architecture targets increasing latency for high precision math operations, execute vertex and pixel fragment shader programs on the same unified processor, decrease latency for low precision texture filtering, depth testing and stencil testing, color blending, etc. Any answers? B, okay. Execute both on the same unified. B. Anyone else? We'll wait one more minute. Okay, let's look at the answer. So yes, it is B, execute both on the same unified processor. Again, looking at it from a historical perspective, you had your vertex processors which were designed for low latency, high precision operations, and your pixel fragment shaders or pixel fragment processors were designed for high latency, low precision texture filtering. So these are kind of contrary to each other, and if these are implemented as fixed function blocks, it's difficult to select a ratio between them. So the primary objective for Tesla was to execute both of these on the same processor. And why is that? It helps in load balancing. So depending on a workload, right, this ratio of these two might change. So if you execute both on a unified processor, you could dynamically load balance depending on the workloads that you have. So that was one of the goals of Tesla. B. And again, none of these were specific to Tesla's goals. Okay, we'll move to a couple of numerical questions. So these I'll probably give you a little more time. A GPU having clock frequency set at 3 GHz and 32 SIMD processors each containing 32 single precision FPUs. What is the peak single precision floating point throughput for this GPU in GFLOPS per second, assuming that all memory latencies can be hidden? And again, assume that it does not support FME. Again, this might not be something that was directly covered in your week's lectures, but think about it from first principles. I'll give you maybe 3 minutes to solve it. 3072. Okay, we have two people saying 3072. Anyone else? Three zero seven two. Anyone else? Okay, if not, let's look at the answer. So before we go to that, again, we're talking about, you will hear of this metric a lot, right? Flops per second. So notice that flops with a smallest is plural for floating point operations. But you'll also see flops with a capital S, right? Which is kind of floating point operations per second. This whole thing is written as flops. So you'll see a lot of GPUs being ranked in this flops. So basically this is sort of indicative of their compute capability, and you'll also notice a precision associated with it. So here it says single precision. Sometimes you will see double precision or FP64, FP32, FP16. Now there are even newer formats like FP8, or even for when we talk about deep learning inference workloads, people also quantize them and run them, right? So they run integers. So then you will see int8 throughput being reported. So this is broadly a measure of compute flops. And similarly, not just for a GPU, you could also report it for a workload. So you'll see that when people talk about, again going back to the example of deep learning, you'll see people say, oh, this neural network has this many flops, this many floating point operations basically. So that's again indicative of the compute of the workload. So now going back to the question, how do we calculate this flop? So again, 3 gigahertz translates to that will directly contribute to the throughput, right? The clock frequency directly. And then there are 32 SIMD processors, so that would get multiplied by 32. Each of those 32 have 32 single precision floating point units. And again, we care about single precision only here. So your peak throughput in for single precision would be 3 into 32 into 32, which is 3072. And that's the answer C. Hope this is clear. Any questions? If not, we'll move to the next one. Amdahl's law is an expression used to find maximum improvement to an overall system when only part of the system is improved. It is often used in parallel computing to predict the theoretical maximum speedup. Amdahl's law for overall speedup is given by overall speedup equal to old execution time by new execution time, which again comes to 1 by 1 over 1 minus fraction enhanced plus fraction enhanced by speed up enhanced. Now the question, so this is the definition of Amdahl's law. The question is like this: 70% of a program's execution time occurs inside a loop that can be executed in parallel. The maximum speed up we should expect from a parallel version of the program executing on 16 CPUs will be dash, and you have 4 options. So again, I'll give you time to calculate this, and if you would like me to go to the previous slide to look at the definition, once you note down things from here, let me know. I can scroll back to the previous slide. 1.351. Okay. Anyone else? $2.909. Okay. Any other answers? Two point 30323. Okay, we have all 3 answers. Any takers for none of the above? 2.9. Okay. Okay, let's look at the answer. So it is 2.9, But again, this was not directly covered in your course material. So let's take a detour and look at Amdahl's law, right? So again, this is a very important concept. So I'll spend maybe 5 minutes talking to you about this. So this Amdahl's law is also referred to as strong scaling. So here the key idea is that your total problem size or the work that you have is fixed, and the speed up that you get by parallelizing it is limited by the sequential bottleneck. So what do we mean by this? Let's take a detailed look. So let's say this is your original task or your process, right? Whatever you want to do. So now there are two parts, A, which is indicated by the red part, and B, which is indicated by the blue part. So this length of the line is proportional to the task or the compute effort. Now, if I were to make B 5x faster, this portion would shrink to this much, right? This is 5 times faster now. But look at the overall length of the line. It is still significantly the same, right? There is some amount that has reduced, but not a lot. Now, let's say I make A 2 times faster. Observe, here it is 5 times, here it is 2 times. But now look at the overall length of the process. It's a lot lesser, right? This is in a way what is referred to by strong scaling. So you have the speed up that you get is limited by the sequential bottleneck. So here, for instance, if this were the sequential part of your program and you could only parallelize this much, then the benefits that you get. So typically there's this very vague notion that, okay, if I have a problem and I run it on one GPU, it's going to take 10 minutes. So let's say I run it on 10 GPUs. So it's going to be directly that much faster, right? It's going to take me 1 minute. But very often that's a misconception and doesn't hold in reality. Why doesn't it hold in reality? Because of this. There will always be a part of your program or your task that is non-parallelizable, and therefore that sequential bottleneck limits the speed up that you get. So even if you throw not 10 GPUs, 100 GPUs at it, it's not going to make that much of a difference. We'll again see an example. So here half your program is non-optimizable. So even if you optimize the other part by 5x or by 10x, the speed up that you get is only this much, right? So let's even, if you look at the speed ups, right, this curve shows you the speed ups. So here on the x-axis is the number of processors or by how much you are parallelizing, and on the y-axis you have the speed up. And the different curves that you see refer to the parallel portions of the program, which is basically 1 minus s. So if you have 100% basically, and there is some fraction of it that is parallelizable, that is your 1 minus s. So the red curve, for instance, is 75% is parallelizable. But look at your curve, the speed up is saturated at 4. So regardless of how many processors you add, your speed up will not go beyond 4. And similarly, if your program is 90% parallelizable, the maximum speed up that you can get is 10, right? So this seems a bit shocking at first, but this is the reality, right? And finally, the green curve, which is 99% parallelizable, still you only get a speed up of 20. So this is strong scaling, and it is very, very difficult to achieve because typically at least some portion of your task is not parallelizable, and that will limit the speed up that you get. So there is one more related idea again that I'll cover, which will be generally helpful when we talk about scaling, right? But not particularly from this course's point of view. So this is referred to as weak scaling or Gustafson's law. So the key idea here is that you increase the problem size along with the number of processors. So remember here, while we increased the number of processors, the work remained the same. Whatever the work was, it was the same. But in Gustafson's law, the difference is that along with the number of processors, the problem size also increases. And once you increase the problem size, what happens? Only the parallelizable fraction of the input work increases with the number of processors. The serial time kind of remains constant. That is the inherent notion behind this scaling, right? So therefore your total time remains constant, as in if you increase the number of processors and your problem size at the same time, the total time will remain constant. So let's say this is your serial work, the red part, and this is your parallel work, right? And basically your runtime is the sum of the two. And now let's say I increase the work itself. So when I say I increase the work, again going back to this definition, only the parallelizable fraction increases. So let's say I increase it to 4 times, right? So you have 1 here, you add 3 more, but the serial part remains at 1. And now you also increase the number of processors, so you can completely parallelize this part, so it comes back to this amount, and the serial work is not parallelizable, but it does not increase as the size of the problem scales. So the serial work remains the same, and your runtime with p processors still remains the same as the original runtime. So that's why it says the total time remains constant. So this is very popularly referred to as weak scaling. So you'll see this notion of strong scaling and weak scaling spoken about a lot. So this is the difference between the two. And any questions? I think this is all I had for today. So we are a little bit early. We finished around 20 minutes early today. So we have a good amount of time for bringing up any doubts or questions. But first of all, this was, so we didn't go back to this question, right? Let's go back to this question now. So here, and you measure speed up as the old execution time divided by the new execution time. So in a very simple example, an ideal one that all of you would think of, let's say the old execution is 10 seconds maybe, and the new execution is 5 seconds. So the speed up is 2. Basically, how many times faster are you executing? Now, the formula for overall speed up with Amdahl's law or strong scaling is given by 1 over 1 minus fraction enhanced. So when we say enhanced, it's about the part that is parallelized, plus fraction enhanced by speed up enhanced, right? So now let's try applying this to the question that we had. So again, 1 over, and I think the problem said 70% occurs in the parallelized portion, right? 70% of the execution time occurs inside a loop that can be executed in parallel. So your P, or in this case the fraction enhanced, is 0.7. So 1 minus 0.7 comes to 0.3, and fraction enhanced is again 0.7, and your speed up enhanced, so remember that you're using 16 CPUs here, so your ideal speed up is 16, right? Because this is completely parallelizable. So if you do this 1 by 0.3 plus 0.7 by 16, I think you get 2.909. You can verify that, and for people who calculated the answer, you can confirm that this is indeed the answer. I think I did that check once. Let me just quickly check it again. Yes, it's 2.909. So is this clear? This might be a little more complicated question. Experience this last law today. We parallelly accessed a website with 100 threads, 100 requests with only a time of 1 request. Okay, interesting. Yeah. So here again, the Amdahl's law is very apparent, right? So if you look at the final numbers, 70% of the program is parallelizable, and you're using 16 CPUs. So you would think in an ideal world you get a speed up of 16, and you would say maybe there are some other effects, so maybe 14 or 13. But the actual speed up that you get is 2.909, and this is the effect of Amdahl's law. It's also referred to as the law of diminishing returns. Basically, you add more and more compute, but the returns that you get from that addition of compute is not really very good. It's because of the bottleneck, the sequential part of the program. So a lot of tools or libraries, when they claim scaling, you have to pay attention to what type of scaling they are claiming, right? Whether it is strong scaling, where the problem size is fixed and you parallelize, or it's weak scaling, where, as someone just said today, you're increasing the work and increasing the processors, right? So that's something you'll have to pay attention to. And if you notice that, you'll see that most libraries or tools claim weak scaling, not strong scaling. Strong scaling is very, very difficult to achieve in practice. Any questions on this? Is it clear how to calculate this? Again, this might not have been there directly in your course content, but it's very, very useful to know. Any questions or doubts, even on strong scaling or weak scaling as such? Okay, if not, yeah, we are at the end of today's content. So again, since we have some, I'm glad you understood it well, and I'm happy that helped. So if you have any other doubts or questions in today's content, please ask me. And since we are at the end of the session, if you have any feedback on the sessions, like you would like more recap, the recap has been very brief probably for the last session and this session. So if you would like any changes in the session structure itself, please also let me know. If you don't have any feedback or any questions, feel free to log off. It's a Friday evening, I know. So have a good weekend, and sorry about the reschedule again, but thank you for joining and keeping it interactive. I will see you next week. And I will hang around for maybe 2 or 3 minutes to see if any of you have questions. So if you have questions, just post them on chat and I will pick them up and explain them next week. Thank you. True, not true answer. Yes, I will do that next class. I think I have an explanation already written up. So I'll just put that in the slide and explain it to you. Any other doubts or questions? Okay, if not, thank you and see you next week. GPU and training AI, yes, definitely, we'll do that, and that's part of your course content also. I think it's explained in week 10 or 11, one of those. So we will definitely explain that in the next week. How to select GPU credits in cloud. Okay, so I haven't used cloud based GPU systems, but typically I think you have, so for CPUs at least I see some notion of core and memory, right? So you typically get a small or a large instance based on the memory that you want. I'm not sure what that metric is for GPU. I can check that and get back to you. Thanks for the question. Thank you. Okay, if you mean the free credits, I think Google Cloud or some of those also give you some amount in free credits, right? I don't know if you're asking about the pricing part of it or the model part of it, but I will look up and let you know. Okay, if there are no other questions, see you next week. Thank you so much.